I guess, can you hear me? Thanks. Okay, good afternoon, everyone. So today is the quiz day. So I'll be showing a slide with the quiz URL at around 4:35. But until then, we're going to start on a new topic, sequential logic. Also, just remember that last Wednesday's lecture, I made a recording for um, you to watch asynchronously. So you must do that because the P set that we'll be releasing in a day or so. So there are two things coming your way, a P set and a design assignment. So the design assignment is going to be on making complicated modules from simple modules. So module number, I guess, 6. And the P set is on module 7, the arithmetic part. So some of the arithmetic stuff was covered in the asynchronous lecture. So please do make sure to watch it. And of course, some of those topics will be addressed in the discussion section also. Okay, so today we have a shift in gears entirely. So early on in the course, you remember we had talked about that there are digital systems which don't have memory. That is, the output depends only on the current input. But then also we have digital systems which are basically the more general case, where the current output depends not only on the current input to the system, but also the history of the input. So this concept is referred to as the system having memory, which, as you might imagine, most systems do, right? I mean, it's not simply a matter of delay, that output is delayed with respect to input, but rather output will depend upon input seen far back, right? I mean, so we're going to examine those kind of problems today. So that's sequential logic, corresponds to chapter 14 in the book. So thus far, we looked at memory-less systems, combinational systems, and we saw a whole bunch of them for doing different kind of operations, including most recently looking at arithmetic and all. So sequential logic, the name given to systems that remember history. The key thing out there is that how much history to remember, right? I mean, in some senses, if a system has been running for a long time and it keeps getting inputs over time, then conceptually, you could say, I need to remember every input that I've ever seen in the past. in the general case. And that is indeed true, but for most systems, we don't need to remember every input that we saw, but rather um, some, uh, just give me a sec, please. Yeah, so rather some subset of it, some function of the inputs we have seen. That's all we need to remember, and that is referred to as this concept of state. So state is something that you may have seen in some other courses potentially also, but kind of the idea is the state is the information that the logic circuit needs to remember in order to perform its function. And then a physically realizable system would have finite state, right? I mean, if the state blows up arbitrarily over time, then of course we can't realize such a system. So there's a concept state, and we'll see more of it later. And then the other issue is, when does the system update the state, right? When do we update the memory that the system has? And they're very broadly kind of two categories of systems that one can imagine. Those which are asynchronous. And by that, I mean that they can choose to update the memory, what is stored, at any time. There is no pattern to it, right? I mean, if I were to examine when the memory updates are happening, they may be, they're highly irregular. Okay, so maybe some important event, like for example, if you think of our brains have short-term memory and long-term memory, and we have this part of the brain called amygdala. And what happens in the amygdala is that whenever long-term memory needs to be formed, essentially it kicks in and causes our brain to remember things. So it could be like when I enter a new room or see a new person or hear something interesting, right? I mean, those kind of things. So those are important events, key moments, and that's when the memory is updated. But a simpler form is systems that are synchronous. And here, kind of the idea is that there is some sort of a periodic signal. We call it a clock, okay? And then kind of the idea is that the memory is updated whenever the clock ticks, okay? So the clock, so this is what the clock in our computer system says, right? I mean, the operation of the system is happening on clock ticks. Every clock tick, the memory elements in the system are updated, okay? And in between, we are doing the computation necessary in anticipation of the next clock tick, right? So in between, basically, we do combinational function, and then when the tick comes, we update the memory and produce the output and move on. Most systems that we implement are synchronous, okay? There are asynchronous systems, but they're a pain to design. And of course, Mother Nature's, like our brains and all, are asynchronous. But we will be interested particularly in systems which are operating on a clock, okay? So if I were to look at the memory of the system, and that's the state, and if I'm observing that state, then that state is updated every clock tick, or potentially updated every clock tick, okay? So that's the key thing. State potentially updated every clock tick. And you can think of the clock tick. We had seen it very early on also in kind of a calendar example. You can think of like the clock as some sort of a periodic signal. And maybe I designate clock tick to be the rising edge. So at every rising edge, the magic happens. We need memory elements. And again, very early in the course, we had talked about that we kind of factor all the memory into kind of a separate type of element within the system. And a very common memory element is so-called D flip-flop, DFF. We'll talk about it later. But there could be other types of memory element. It could even be a regular RAM, or in theory in our computer systems, if you have lots of state, it may be stored on disk or flash or whatnot. Anything which can preserve data across across clock ticks can serve our purpose. We'll talk about how to design and analyze and optimize sequential logic circuits, these type of circuits, particularly those which are clock synchronous circuits. That's what our focus is going to be. There are other designing asynchronous circuits, clockless circuits is pretty tricky, and I don't think there are any courses that I can suggest at UCLA. It's kind of a more esoteric area of design, but if you get into this computer design as a profession, you might encounter them. Okay. So what we are going to go over is the concept of state, concept of synchronous sequential logic, look at D flip-flop, and how do we analyze synchronous sequential logic, in the sense that if I give you the circuit for the logic diagram of a synchronous sequential logic, then how do we analyze it? What does it do? So let's look at it. So we had seen this slide before. Combinational logic is output, right? This is the output vector, is a function purely of the input, right? So I have m bits of outputs and I have I bits of input. So output is a function of I, and this function is just memoryless, right? I mean, if I changes, if even any of the I's change, then O will change, right? So our AND gate, everything that we have seen in the course thus far, the stuff we do with Karnaugh maps and all, are combination logic. Sequential logic have memory. So kind of the idea is, one way of thinking about is that the sequential logic have a combinational part to it, which takes the input, okay, here, produces an output, but then it also remembers stuff. That's the memory. And what is happening is that this combinational logic, faced with any change on the input, so it has access to both. It has access to what is stored in the memory, and it has access to the input coming from the outside world. And based upon that, it updates the output, and it can also update what goes into the memory, okay? So it can write to the memory, and it can read from the memory. Right? So you can think of this arrow representing write, and this side representing read. And this can happen in general in complicated ways, which is whenever either what is in the memory changes or whatever is coming from the outside world changes, that can cause a change in output and cause an update in the memory. In a synchronous system, we have a clock. Yeah, go ahead.
So an state can count both as an input and output.
Can you repeat the question, please?
Oh, an state can be counted both as an input as an output.
Correct. So so you can think of it as this is a next state. We'll see that term before. We'll see that term shortly, and you can think of this thing as the current state. Okay, so state is a memory. At any point in time, I can read what is currently there, and that feeds into this combinational logic, and the combinational logic also looks at what is coming from the outside world. So this is coming from outside, and then based upon that, it can update what it is sending to the outside world, and or it can update the next state, which is going to go into the state memory. Okay, so that's how we can think of a sequential logic, right? And so they have this kind of a feedback loop through kind of a memory structure. So state, the concept of state is that it captures the relevant information about the past, right? That is, in order for the system to perform its functionality, it's not as if we are just blindly recording everything that we are seeing on the inputs coming from the outside world. We could if we had infinite resources, but real systems don't. So we are going to extract something, right? I mean, let's say, for example, my task was to output if let's say in was 1 bit, and my task was to output whether the number of ones on the input thus far is even or odd, right? So let's say my output was a 1 bit, and I want to just remember, I just want to output 1 whenever the number of inputs I have, number of ones I have seen on the input since the system powered up is even or odd. So in that case, what do you think I need to remember at any given moment in time? If my job is simply to say, oh, until now I have seen an even number of 1, and then I'll output a 1. And if I've seen an odd number of 1, I'm going to output a 0. If that's my job, what should I remember about the inputs?
The amount of ones seen?
Well, so amount of 1 seen is possible, but the problem is that will grow infinite, right? If the system keeps running for millions of years, let's say, then that will grow unbounded. Can you think of a way that I can remember a finite number of
Could you do a modulus of that?
Modulus with what?
Of like the amount of ones that you see. So it would go like 0, then 1, it would like flip-flop.
Right. So so can you be more precise about it, right? I mean, modulus. So the answer is, all I need to keep track is, until now, have I seen an even number of 1s or odd number of 1s? That's just 1 bit, right? And then next time I get a new 1, then if thus far I had seen an even number of 1s, then I will flip. If I had seen an odd number of 1s, I will flip, right? So every time 1 comes, I kind of toggle a 1 bit that I have. And so that way, to perform this task, I only have to remember 1 bit. And the meaning of that bit would be, have I seen an even number of 1s thus far? So as you can see, this problem, I could have said, yes, store everything that I have seen, or store the number of 1s I have seen, but those are all unnecessary. All I really need to store is that 1 bit. But not all problems are like that. There are problems where I truly need to store kind of the entire history. Okay, can you think of some problem where I have to store the entire history of what I'm observing? Let's say n is just 1 bit. Okay, can you think of a function where, for me to provide the output for it, I have to store everything I've seen thus far?
Like if the output depends on, like if we have seen this input state before.
Can you be more precise about it? Well, not good. So give me a mathematical function of the input. Mathematical function of the input, which would require me to remember all the inputs I have seen over time. So I'll give you an example. Think of all the input bits which are coming in one by one. Let's say the first bit which comes in, think of it as a least significant bit. Next bit which comes in, I grow it, right? I mean, I keep adding bits. So I think of the input I have seen thus far as a number. And if I say output a 1, if the number you have seen thus far is prime. Right now, of course, if the first bit I got was a 0, that would be easy. But in general, I have to remember everything that I have seen thus far. Okay, so that's one. Another example is, if the number of, if you think of all the bits I have seen thus far, is it a palindrome? Anyone knows what a palindrome is?
Yeah, if the number reads the same from front to back and from back to front.
Back to front, exactly, right? So think about it, right? To output a 1, if the bits I have seen form a palindrome, I have to remember everything. So there are obviously tasks which I cannot solve with a finite amount of states. But then also we saw there are tasks which I can solve with a finite amount of states. Of course, any system that we are going to do, real life will have to have that finiteness requirement, right? So we're particularly interested in things which can be done with a finite number of bits needing to be remembered. Okay, so we'll see more of these. So let's look at a simple asynchronous sequential circuit. There's no clock in this, but it has memory in it. Okay, and remember we had seen earlier in the course that if the circuit is acyclic, then it can never be sequential. But if the circuit is cyclic, then it may be sequential. And this is an example of a circuit which we'll shortly see has memory in it. Okay, so all here it is, there's a NOR gate here, and this is actually also a NOR gate, right? De Morgan's theorem. So I have two NOR gates tied up in this manner. So now if you think of the equation of Q, then Q is not R ANDed with not X. And then I can expand X. X is not of S or the previous value of Q. And so the equation of Q becomes Q is not R and S or Q old, right? So essentially Q depends upon its own previous value. And therefore, you can think of Q as our state, right? So we are remembering, we are depending upon that. So a combinational logic, the output depends only on the input. In sequential logic, the output depends upon history, and therefore, in general, you can say the output depends upon its own prior value, or but then the prior value in turn depends upon previous inputs. So by transitive argument, you can say Q depends upon what we have seen thus far. So in programming terms, we can say basically saying if R equal to 1, then Q is 0. Else, if S equal to 1, then Q is 1. Otherwise, Q is equal to Q old. So what's happening out here is R is like a reset. It's resetting Q to 0. S is like a set. It sets Q to 1, provided there is also not already a reset present. And then finally, other cases, that is, neither one of them is 1, neither R nor S. So S and R are both 0. Then the system hold its value, right? That's what's happening. It's holding its value. So that's the memory part. So if I look at that state table, so you can think of now a truth table, except that we call this thing state table because here I have state. So I need to remember the old value in the state or current value in the state and the new value in the state, right? I mean, so my combinational logic, right? This is the combinational logic part, right? That's the combinational logic. It has 3 inputs, right? It has R and S coming from the outside world, and then it has this Q old, which is the state, right? Q old or Q current, depends upon how you define it, same thing. Okay, and then this Q or the Q next is a new value, right? So what's happening is if R is 0, S is 0, and Q old is 0, then Q is 0, because remember our logic was Q is Q old if R and S are both 0. Likewise, if R is 0, S is 0, and Q old is 1, then the new value of Q is still 1. So Q is held to its value. If R is 0, S is 1, and then Q old doesn't matter because I'm going to unconditionally make Q equal to 1. And then finally, if R is 1, then independent of what S and Q old are, I'm going to reset the output. So as you can see, this thing, the X here means whether it's 0 or 1. So it's essentially these are our cubes in the combinational logic, right? I mean, yeah, it's a bigger prime implicate. I'm merging rows. So 1xx means 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. All of them, Q is 0. Likewise, 0, 1x means 0, 1, 0, and 0, 1, 1. For both of them, Q is 1. So the full truth table, you can write it as 8 rows, but this is just a more compact notation. So in case of sequential systems, for the combinational logic part, we call the truth table to be state table. Okay, but this is basically nothing but a truth table. These are the inputs. And this is the output. Right now, our state has only 1 bit, but more generally, Q old and Q, they correspond to some K bits, because I may need to remember more than 1 bit. Okay, so that's an RS flip-flop. It's a widely used function, so it has its own circuit symbol, SRQ, and then Q bar usually in these circuits, not only do we output out, but we also output its complement. So Q bar is nothing but the complement of Q. And what it is doing is it is latching information in place. That is, it holds information in place if S is 0 and R is 0, and therefore it's called a latch. That's why RS, reset, set, latch. R has higher priority, so R comes first, then S. If it was the other way around, then we would call it SR latch. That means set would have priority. Latch means it holds its value, and there is oftentimes people also refer to it as a flip-flop, although usually the term flip-flop is used when we have a clock also on it. Okay, so so that's what we have out here. So let's look at how this behaves. Okay, let's take an example. So let's say we are going to view over time what the circuit is going to do. So we are starting out with R and S, and Q is some unknown value X. Okay, so this X out here means someone is either 0 or 1. Okay, so let's move. So at some time t1, R goes to 1. And since R goes to 1, so now we are in 0, R equal to 1, S equal to 0. And therefore, by the final row, output now at that point becomes known. It becomes 0 after a teeny delay. Okay, so there will always be some circuit delays. Okay, this arrow that you are seeing out here is basically indicating causality. Causal dependence. In other words, we are saying it causes. So R going 0 to 1 causes Q to become 0. If Q was already 0, then of course Q remains 0. But if Q was 1, it will become 0. Okay, let's move on. Let's say at a later point in time, R goes back to 0. Well, that shouldn't change anything, because if R is 0, S is 0, Q holds its value. So Q holds its value. Then at T2, S becomes high. R is 0, S becomes high. So we are in this row. And therefore, Q will become 1. And that's why you are seeing Q become 1. And so again, we have this causes kind of arrow out here. And keep moving like this. Again, after a while, maybe R goes, okay, so, and then S goes, and so on and so forth, right? So given some evolution of R and S over time, you can draw what happens to Q. And that's what we are seeing out here. Okay, so okay. So I can, so that's what RS slash does. I can also draw it differently. So more typically you would see it drawn the way I have on the right hand side, but convince yourself it's exactly the same circuit, right? Because this is a NOR gate, and I've just plotted the NOR gate like this out here. Okay, so you will see this kind of a butterfly type arrangement to be more common. Okay, so now where can we use that? Okay, so a good example is that, you know, when you fly plane, you have these call buttons, right? For the flight attendant. So I can press the call button, the light goes up, and then usually there's a cancel button. And if I press the cancel button, or flight attendant presses the cancel button, then the light goes off. And in between button presses, the light holds its value, right? If I press the call, then the light remains on, and if when the flight attendant comes, presses cancel, light becomes off and stays off until the next time. Okay, so the starting state is light is off. I press the call button, light turns on. I release the call. Now the light remains on. So what is the state out here? The state out here is saying the last button pressed was the call button, right? That's what I'm remembering. What was the latest button pressed? Was it call or cancel? So in my logic, there is memory, which is basically saying, hey, the last button pressed was the call button. and then we cancel, the light turns off. If I press both of them simultaneously, what happens in the SR latch? You recall, we just saw a short while ago. If R and S are both 1,
Still 0?
still 0, right? Because R has the priority. You could imagine another type of latch where S has the priority, right? Okay. So we talked about this. Okay, so this is an example where you see a memory behavior, but without any clock, right? Which I described, right? This is purely asynchronous, right? Whenever you press call and reset, set and reset, some magic is happening. Okay, so more generally though, we deal with far more complicated systems, and this is where we get into the world of synchronous sequential logic, where we have a clock and the state updates only happen when the clock ticks. So that is, I will write to memory only upon as a result of clock tick. That is, inputs may change, but the effect of those input changes into a new memory being formed will only happen at a clock tick. Okay. And again, in real systems, there will be circuit delays, so a little bit after the clock tick. So those are called synchronous sequential circuits because they're sequential, they have memory. They're synchronous because action is synchronized with the clocks. So with RS latch, the state changed at arbitrary times, depending on what inputs changes, how fast the various gates were, and all this was asynchronous. Unfortunately, these circuits are very hard to design in more general cases. I mean, what we had was a super simple example, but more complicated behaviors can be pretty tricky. Having said that, there are very valid uses of these circuits, particularly in where speed is of particular essence, so you see them in like arithmetic units of processors and all, and handshake logic and things like that. So they're designed, but one has to be super careful because it's very easy to get them wrong. I don't teach them beyond kind of these simple things, okay, but they exist. So synchronous one, state information is stored in memory, but it is updated only at the tick of the clock. So kind of the idea is when the clock tick comes, then at that point in time, the combinational logic part of the sequential logic is going to, the value it is producing for the next state, at that point in time, we write it into the memory. So the tick could either be, in most cases, we define the tick to be edge of the clock. And usually we'll pick one edge, either the rising edge or the falling edge of a periodic binary digital signal. Okay, the period doesn't have to mean the clock has to stay high and low equal amount of times. It's not 50-50. It could be that it stays 1 for a longer time than it does 0, but the period is fixed. So if I define my clock to be rising edge, then the gap between two rising edge is a constant, or supposed to be a constant. There are also systems where the tick is defined in terms of the level, like when clock is 1 as opposed to when clock is going up. Okay, but we are not going to study those. Okay, so what looks like for us a sequential circuit then is as shown out here, which is the state has a clock. The clock signals are shown by this triangle, and you will see two kinds of clock signals, those which look like this and those which look like with a bubble. This means rising edge, this means falling edge. Okay, so that is the state is updated at the falling edge versus rising edge. Okay, so that's kind of the idea. So imagine some sort of a state memory which at the clock tick, whether rising or falling, in our example rising, writes whatever is present on these lines, it stores it. Okay, otherwise this guy may be changing out here, the state is unperturbed. But the moment clock comes, then whatever is on the wires out here at that point in time gets stored into the memory. We'll see later in the course that there are again some delays and all to be accounted for. We have to make sure that whatever is on the wires out here is stable a little bit before the clock and remains stable a little bit after the clock. But that's a implementation detail. At an abstract level, you can say that when the rising edge comes, at that point in time, whatever is on these wires get clocked into the state. Okay, so we are nearing the time of the quiz, so I'm going to stop at this slide, but basically that's what's happening. There's a period, which is the gap between two rising edge, and then falling edge, rising edge. In this particular case, the rising edge is our the edge at which the memory is updated. Okay, so it's a good time to stop. So the way the quiz is going to work is each one of you is getting a personalized notebook, very much along the lines of what you got for the PSET. Here is the URL, and so hopefully you guys are able to capture this, and I think we are also going to be posting it on Piazza very shortly. If Goffin should be doing it any moment. Okay, he just did it. So when you go to the spreadsheet, make sure, absolutely sure, that you are downloading the link corresponding to your name. It has to be, it's the same as the row. So you will see the same. If you are in row number 35, then your URL, that the file that you will download should say _35 in it. And I'm going to stop the recording at this point here, and I'm going to be on Piazza. On Piazza, you will see on the top left live Q&A. So TA and I will be there to answer any questions. Stop time is, or you have to upload it by 5:50. So we are giving you 15 minutes slack to download and upload. Don't mess with any cells other than the answer cells. Super important. And if you are running into any
quick question.
Yeah, go ahead, please.
So on the document for all the quiz assignments, I can't download my quiz file.
What do you mean you cannot download?
Like I click on the link and it just redirects me back to the Excel sheet, so I can't download it.
Yeah, same.
Yeah, same with me.
I have that issue too.
I think it's getting blocked. I had
It's
to
insecure
click
for
something
me.
to make it download.
No,
You
when
you can
click
copy the
on,
link and paste
you
it
click
in
on-
new tab.
yeah, you click on the link and then you will
Oh, you copy paste the link.
Yeah,
Okay.
copy the link,
Okay,
open
thank
a
you.
new
Thank
tab,
you.
paste it, and then access it.
I'm just getting a redirect that's not going anywhere from the Google Sheet.
Yeah, same here.
You can copy and
Copy the
paste.
link in there and paste it in a new tab.
yeah, you just
Yeah,
copy the
both
link
the
and
same
paste.
redirect. Whether
I
or not
tried
I
that.
click on it,
Yeah, it still doesn't work.
It still doesn't work.
Let me come on to. Can one of you share your screen and show me what you're doing? Yes, you can leave if everything works. It should work. Those of you are seeing redirect, you're doing something wrong. Just copy, right click, copy the link. It should be a Google Drive link.
So I can share my screen to see or to show what's happening, right?
Yeah, share your screen, please.
So I copy the link and then I paste
No,
it.
no,
Or sorry.
no, you are copy
Yeah.
the link. No, yeah,
Copy link address. And then it does this and it just stays
no,
here.
no,
I'm getting the same error too.
no, we are not copying properly. Okay, so go back out there. Okay, click on that, click on your link.
Do I need to copy this?
And no, select the
Oh.
text that says right next to redirecting to.
Redirecting, yeah.
Yeah, that one. Now
Yeah.
paste that in the URL.
Yeah.
It's gonna tell
Okay.
you to keep it and press keep when
Okay.
it asks you.
In the download icon,
All right.
download.
Yeah. Okay. Thank you.
Okay. Okay, see you guys on Piazza.
Wait, I have a quick question.
Sure.
So after I download like the link, right? It says like keep, but like where do I open it as? Like there's no option to open it in Google, like in Google Colab or anything.
No, you'll have to either upload it to Google Colab or use Visual Studio or Jupyter Notebook, just like you did for PSET1. It's a Python notebook, IPYNB file.
Oh, I see. Okay.
Yeah, right. I mean, the file you are downloading is an IPYNB file, and just like you did for PSET1, it's exactly the same process.